The night of July 1st, 2025, the Rio Hurtado station of the Asteroid Terrestrial Impact Last Alert System, ATLAS, recorded a faint, fast-moving smudge in the southern sky. Follow-up images from ATLAS telescopes on Mauna Kea, Haleakala, and South Africa, plus frames extracted from Caltech's Zwicky Transient Facility, showed the object had been hiding in star-crowded fields since mid-June. Orbital solutions refused to close. An eccentricity above 1.0 meant the visitor was not bound to the Sun. When the Minor Planet Center confirmed the numbers on July 2nd, the designation 3I/ATLASC/2025N1 became official, the third known interstellar object after 1 I/Oumuamua and 2 I/Borisov, and the first discovered by an automated planetary defense survey. Trajectory analysis traced the comet back toward the constellation Sagittarius, the Milky Way's crowded core. Its inbound speed on discovery, about 61 kilometers per second, or 137,000 miles per hour, already exceeded the local escape velocity. As it falls sunward, the velocity climbs to more than 87 kilometers per second, fast enough to cross the average Earth-Moon distance in under 5 hours. The asymptote of its hyperbola implies that once it recedes beyond Neptune in 2026, it will wander interstellar space for tens of billions of years before any star perturbs its course again. The orbit plane is tipped only 5 degrees to the ecliptic, yet runs retrograde, so the comet cuts across the paths of the planets like an oncoming car in the wrong lane. A geometry that gives astronomers unusually long continuous visibility. Perihelion arrives on the 30th of October, 2025, at 1.4 astronomical units just inside Mars's orbit, followed by an outbound leg past Jupiter in March 2026 and Saturn in mid-2027. Because the Earth-Comet minimum distance never drops below 1.8 AU, 3I/ATLAS poses no impact threat, but its slow apparent motion and months-long window make it a dream target for telescopes in every wavelength. Even the first stacked ATLAS frames hinted at a diffuse halo. Confirmation came 2 July, when the Lowell Discovery Telescope and Canada-France-Hawaii Telescope resolved a tiny but definite coma roughly 3 arcseconds across. That coma marks sublimating ices, proof that 3I/ATLAS is an active comet rather than a bare rocky fragment like Oumuamua. Hubble observations on 21st July measured a teardrop-shaped dust cocoon roughly 9,000 kilometers long, surrounding a still unresolved nucleus. Using standard dust-to-gas models, researchers constrained the solid body's diameter to between 440 meters and 5.6 kilometers. The wide range reflects unknown albedo and activity level, but even the minimum puts it comfortably larger than 2 I/Borisov's half-kilometer core. Spectra from the Nordic Optical Telescope, Gemini South, and the Very Large Telescope revealed strong C2 and CN fluorescence, plus an unusually high CO, 2 to H2O ratio, chemistry consistent with ices formed far from a parent star, perhaps inside that system's analog of our Kuiper belt. Preliminary Webb/NIRS PEC data released 6 August show absorption bands of CO ice deeper than any seen in solar system comets, reinforcing the picture of formation at temperatures below 25 Kelvin. Such a volatile, rich inventory resembles but is not identical to Borisov. It suggests diversity among outer disk reservoirs around other suns. Brightness evolution has followed a near textbook R to the power of -4 law, modified by sporadic 0.3 magnitude outbursts every few weeks. Those flares coincide with spikes in CN emission and increases in dust production rate, indicating pockets of supervolatiles venting as fresh layers rotate into sunlight. If current trends hold, the comet will peak near magnitude 10 at perihelion, easily accessible to backyard telescopes with CCD cameras. Outreach groups worldwide have scheduled real-time webcasts so the public can watch an interstellar body brighten day by day. Because perihelion lies near Mars's orbital radius, mission planners realized early that spacecraft already at the Red Planet could provide an unprecedented close look. On the 3rd of October, 2025-3, I/ATLAS passes just 29 million kilometers from Mars. ESA's Trace Gas Orbiter and Mars Express, along with NASA's Mars Reconnaissance Orbiter, MAVEN, Perseverance, and Curiosity, are all executing target of opportunity campaigns. Ultraviolet spectrometers will map hydrogen escape, infrared imagers will constrain grain temperatures, and high-resolution cameras may glimpse structure in dust jets. The geometry is similar to Comet C/2013 A1, Siding Spring's 2014 flyby, but this time the visitor hails from another star. Meanwhile, farther afield, ESA's JUICE spacecraft en route to Jupiter will monitor the comet during November from a vantage 600 million kilometers distant. JUICE's near-infrared mapper can compare the 3I dust spectrum with that of Jovian irregular moons, probing whether similar compositional classes populate circumstellar and circumplanetary debris reservoirs. Flights of NASA's Hubble, Webb, Swift, and soon-to-launch SphereX are time-sharing orbits to catch complementary wavelength ranges, creating the most extensive observing campaign ever devoted to a single cometary body. ATLAS data, combined with ZTF pre-coveries, permit backward dynamical tracing roughly 2 million years, enough to estimate 3I/Atlas entered the Sun's sphere of influence with a barycentric velocity of 26 kilometers per second. Monte Carlo integrations identify a handful of plausible source stars, with the highest likelihood pointing toward a K-type dwarf 17 light-years away in Sagittarius. Although uncertainties remain large, the exercise illustrates how each additional interstellar object helps map gravitational streams in the local spiral arm, turning the solar system into a particle detector for galactic dynamics. Comparisons to its predecessors reveal both continuity and surprise. Oumuamua was small, spectrally neutral, and exhibited non-gravitational acceleration without detectable gas. Borisov looked like a typical long-period comet, but carried unusually high CO relative to water. Atlas shares Borisov's activity, yet shows even richer CO2 and stronger dust-to-gas coupling, plus a nucleus size at least an order of magnitude larger than Oumuamua's. The emerging pattern hints that volatile-rich bodies may dominate the interstellar flux, simply because icy mantles survive ejection shocks better than brittle rock, but the sample is still far too small for firm statistics. Planet formation models predict that every newborn giant planet scatters tens of Earth masses of icy planetesimals into interstellar space. Given the galaxy's hundreds of billions of stars, astrophysicists estimate the Milky Way contains something like 10 to the 26th comet-sized wanderers. Around one such body should cross Earth's orbit every few months. 3 I/ATLAS suggests survey sensitivity is finally approaching that theoretical rate. Within a decade, the Vera Rubin Observatory's legacy survey of space and time should raise detections from 1 per few years to dozens per year, letting researchers build a taxonomy the way asteroid science moved from series to 500,000 catalogued orbits. Each interstellar object is also a laboratory for prebiotic chemistry in extreme environments. Stellar irradiation during millions of years in deep space can polymerize simple ices into complex organics. Impacts of such bodies onto young terrestrial planets could seed surfaces with ready-made carbon scaffolds. By measuring isotopic ratios, D/H in water, 12C/13C in CO, 14N/15N in CN, astronomers test whether building blocks for life are universal or vary star to star. Early ALMA data on 3I/ATLAS hint at a D/H, twice Earth's oceans, but within the range of Oort cloud comets, supporting theories that the isotopic mix of volatiles derives more from disk temperature than stellar metallicity. Instrumentation limits mean remote sensing can probe only the outer skin of the nucleus. The Holy Grail is a sample return mission. ESA's Comet interceptor, scheduled to wait at Sun-Earth L2 after a 2029 launch, was designed for exactly this scenario: sprint to a newly discovered long period or interstellar comet, escort it through perihelion, and deploy subprobes. Engineering teams are updating flight software to handle velocities twice those originally anticipated, because 3I/ATLAS demonstrates how fast true interstellar comets can be. Concepts from NASA's Interstellar Object Explorer study propose solar electric propulsion stages combined with Jupiter gravity assists, able to match approximately 70 kilometers per second relative speed if launch occurs within 18 months of discovery. Beyond science, 3I/ATLAS resonates culturally. Planetaria are scheduling live dome shows tracing its path. Museums display the discovery images beside artist renderings. Media headlines call it the comet from another sun, rekindling the sense of cosmic connectedness, first sparked by Oumuamua in 2017. Yet the novelty is already fading into normalcy. 3 such objects within 8 years hint that the solar system is less an isolated island and more a busy crossroads of galactic debris. Logistically, the campaign is a rehearsal for planetary defense rapid response. Within 24 hours of confirmation, the IAU's Minor Planet Center distributed ephemerides. Within 48 hours, NASA's Planetary Defense Coordination Office issued observer calls. Within 72 hours, spacecraft teams drafted pointing plans. The process compresses what once took months into days. Experience that will be crucial not only for future interstellar science targets, but also for any inbound hazardous asteroid discovered late. For computational astrophysicists, 3I/ATLAS provides a rare benchmark. Dust dynamical models must cope with hyperbolic trajectories, where solar radiation pressure and Lorentz forces change grain orbits on timescales of hours. Gas dynamics codes test sublimation under cosmic ray-altered crusts. Laboratory chemists simulate irradiation of mixed CO-N2-CO2 ices at 10 Kelvin to replicate its spectra. Each discipline gains a data point that only a naturally delivered sample from another star could supply. If perihelion activity lifts the dust production past 10 kilograms per second, the comet's tail could stretch tens of millions of kilometers, briefly rivaling mid-brightness classical comets. Because the orbital inclination is low, Earth's line of sight crosses the orbital plane in mid-November, offering a chance to image tail structure edge-on and study grain size sorting in 3 dimensions. An experiment impossible for most solar comets whose orbits stay well above or below the ecliptic. Should any fragmenting outburst occur, The relative velocity of ejected pieces, tens of meters per second, will be negligible compared with the comet's 80 kilometers per second heliocentric speed. So, debris will form a thin ribbon along the track, not a spreading fan. Meteor specialists will scan radar returns for hypervelocity micrograins intersecting Earth's orbit. None are predicted this passage, but future interstellar comets may seed visible exoshowers, meteors entering at 70 kilometers per second and distinguishable by their radiant direction near the solar apex. As the outbound leg lengthens, ground-based spectroscopy will shift from volatile bands to forbidden oxygen and sodium lines tracing photodissociation products. Even after the nucleus fades beyond reach, the telescopic trail of atoms offers weeks of additional data to refine mass loss rates and constrain total inventory. The comet becomes, in effect, its own exhaust plume experiment on how interstellar ices respond to a mid-G type star. From a philosophical perspective, every interstellar object is a physical letter from an unknown sender. Chemical fingerprints are the words, isotopic ratios the dialect, orbital vectors the postmark. 3 I/ATLAS's letter tells of frigid nurseries, violent scattering, eons of solitude, and at last a brief flash of sunlight in a borrowed sky. Reading it enlarges humanity's sense of community from 8 planets and a few dwarf worlds to the entire galactic neighborhood. In December 2025, 3 I/ATLAS glides 270 million kilometers from Earth, dim, rosette-tailed, already accelerating outward past 60 kilometers per second. Amateur astronomers will record final light curves. Professional observatories will harvest last spectra. Databases will lock in the definitive orbit. Then the comet will fade below detection, receding toward the cold transparency of interstellar night. But the legacy of data will persist in petabytes of images, spectra, and telemetry. When historians look back, they may regard 3 I/ATLAS as the object that transformed interstellar object studies from curiosity into routine science. An event observed by fleets of spacecraft, dissected across the electromagnetic spectrum, and used to fine-tune future rapid response missions. It reminds us that the galaxy is not a distant abstraction, but a living environment exchanging matter and stories across light years. The next messenger could appear any month, any night, on any image. Thanks to Atlas, Rubin, and the vigilance of sky watchers everywhere, we will notice. And the dialogue between stars will continue,